in Grand Teton National Park yesterday in the area of the Signal Mountain Summit Road Sunday afternoon. Grand Teton National Park rangers and Teton County search and rescue personnel responded and awaiting. Park biologists believe this was a surprise encounter.
It began with a fissure. The earth cracked open in Grand Teton, a yawning tear cutting through the soil, splitting terrain that for millennia seemed solid, unshakable, part of the mountain's proud backbone. What first might appear as a curious geological oddity now carries a far heavier weight. A red flag raised by the United States Geological Survey, a warning that the land itself is signaling a danger more profound and insidious than mere crevasses. Before we start, smash the like and subscribe buttons for more updates. From satellite images to field observations, scientists have detected signs of sudden ground displacement in the region. The crack stretches across the landscape, irregular in depth and width, sometimes mere inches, sometimes gaping to several feet. But the true threat lies not merely in the cleft itself, but in what it represents. Shifting stresses in the crust, unseen forces gathering momentum, tectonic energy that may be silently reconfiguring the faults beneath the grand peaks. What seems like a fissure is more like a whisper of collapse, a harbinger of Earth's raw and restless mechanics. Geologists descended upon the site, their instruments whirring, measuring minute changes in the terrain. Strain meters, GPS stations, and laser ranging devices tracked ever so slight motions, tilts, uplifts, and subsidence. Early assessments hint at active tectonic strain along the Teton Fault Zone, which underlies much of the rugged mountain front. That fault has long been understood as a normal fault, one in which one side of the crust drops relative to the other due to extensional tension rather than compressional squeeze. Over geological timescales, movement along it has sculpted the range, tugging and lifting slabs of crust in episodic upheavals. Though the Teton Fault has not produced a major surface-rupturing quake in thousands of years, its history is written in the layers. Trenching and stratigraphic studies reveal repeated slips of magnitude 6.6 to 7.2 over the past 10,000 years, spaced irregularly but enough to suggest that the fault remains active. Now, this sudden crack may be part of that ongoing narrative of stress release, or warning of something more immediate. When Earth splits like this in a mountain range, many phenomena can be at play. Seasonal freezing and thawing, especially in high-altitude climates, can cause frost wedging. Water seeps into tiny fractures, freezes, expands, and pries them open inch by inch. Over time, such action can widen cracks, encourage rockfalls, loosen soils, yet this process is gradual, cyclical, predictable in mountain zones. The magnitude and recency of this opening suggest a deeper cause, tectonic strain, perhaps augmented by unseen pressures from below. Underground, stresses accumulate along fault planes. Where rock is brittle, fractures propagate sometimes quietly, sometimes violently. If a slip occurs deeper down, perhaps along a hidden branch of the fault, it can send reverberations upward, loosening overburden, destabilizing zones long settled. The crack at the surface may in that way be an unlocking of stress trapped in the subsurface. Complicating matters is the possibility of fluid pressures. Deep groundwater or hydrothermal fluids can march through pore spaces, lubricating fractures, reducing friction, creating zones of weakness. At sufficient pressure, fluid influx can trigger slips that would otherwise remain locked. In mountainous regions, snowmelt or external precipitation may percolate downward, entering deep fractures and altering pressure balances. The opening in Grand Teton may thus be not only a passive response to tectonic stretching, but an active conduit for fluid motion altering fault stability. The geometry of the crack is telling. It is not a straight line, but a jagged pathway, bending with the underlying geology. In places, the walls slope inward. In others, they flare outward, reflecting heterogeneities in rock type, variable fracture toughness, and subsurface fault complexity. Some segments show parallel cracks, twin fissures flanking a central zone, suggesting zones of shear strain or tensional splitting. In sections with steeper walls, debris has begun to fall, soil and rock tumbling into the void, enlarging the gap in a subtle feedback. Scientists have warned that the fissure is more than it appears. Though superficial damage may seem limited to terrain scarring, small landslides, or slumping of soil edges, the deeper implications are concerning. If fault movement beneath continues unseen, sudden rupture could propagate upward, producing larger displacements or triggering secondary cracks in nearby slopes. The crack might mark a zone of mechanical weakness ready to propagate outward. What makes this situation more dangerous than it looks is the subtlety. Unlike a dramatic earthquake where shaking is immediate and its epicenter clear, the processes here may unfold slowly, creeping over months or even years, going unnoticed until cumulative deformation reaches a threshold. Infrastructure, roads, trails, observation platforms may suffer incremental damage, fissures widening, support foundations shifting. A seemingly stable ridge might one day weaken enough to collapse, sending rock slides downslope without warning. Fauna and vegetation also sense stress before humans do. Tree trunks may begin to tilt, roots stretch for anchorage, soil cracks disrupt root zones. Springs or watercourses can redirect as subsurface conduits realign. These biological cues may precede visible hazard, but they are subtle signals only a seasoned observer might catch. In steep terrain, the risk of slope failure compounds. The crack in Grand Teton lies on mountainous flanks where gravity is a constant force. If further tension or slip occurs, mass wasting may accelerate. Undercutting at the crack's base, especially during precipitation, could destabilize overlying rock. Once a block detaches, it may cascade downward, knocking loose further rock mass and expanding the damage zone. Thus, what seems a limited fissure could become a landslide initiation zone. Moreover, the crack connects to an active fault system. The Teton Fault, though not frequently rupturing in recorded history, possesses the capacity to deliver strong quakes. Sudden fault slipping could propagate to adjacent segments, reactivating previously quiet branches. A rupture initiated at depth might migrate upward and outward, enlarging fissure networks across ridgelines. Thus, the fissure becomes both symptom and possible seed for larger faults to awaken. The warning issued by the USGS underscores that observation and monitoring must intensify. It signals that what might superficially read as cosmetically dramatic is in fact geologically potent. The fissure is a live indicator of shifting stress fields in the crust and may presage a more significant rupture. The danger is insidious. It may persist in dormancy, then surprise with acceleration when thresholds are crossed. Such a phenomenon also provokes re-evaluation of hazard maps. Zones around the rift now demand re-examination. Regions once deemed stable might lie closer to active strain than assumed. Tourist routes, park facilities, recreational trails, even viewpoints perched near the cleft need reassessment of safety margins. The crack thus forces planners, park managers, geologists, and civil engineers to reconsider what is safe ground in a sitting where the ground is changing from below. Public perception often underestimates phenomena like this. A crack in dirt looks static, like a scar in the landscape, not a living device of tectonic dynamics. Yet its existence is dynamic. It may widen slowly, creep, feed into other cracks, or erupt in sudden jumps. The danger lies not only in its present form, but in its latent potential. One of the trickier aspects is that the most dangerous processes are hidden. Deep subsurface strain is invisible without instrumentation. Fault lines may shift below unfractured rock, and only later transmit that motion to surface features. The crack visible now might mark the edge of a more extensive subsurface rupture zone. The magnitude of motion along an unseen fault could dwarf what's shown at the surface. Because of that, predictive capability is limited. Scientists cannot yet say with confidence whether the crack is stable, slowly evolving, or accelerating toward rupture. But they know enough to concern themselves. Patterns of deformation, once established, tend to continue or escalate, not reverse abruptly. The worst-case scenario is a cascading event where an initial fissure slip triggers adjacent faults, causing sequential breaks, each feeding the next. That complexity would magnify damage potential far beyond the initial crack's footprint. The geological context of the Grand Teton and the Teton Fault intensifies concern. This range lies along active zones in the greater Rocky Mountain region, where crustal deformation continues. The Teton Fault runs along the eastern side of the range, forming the dramatic uplift that creates the sharp peaks that tower above Jackson Hole. Past movement along that fault has shaped the current topography. While most recent major slips were thousands of years ago, the fault remains classified as active, meaning that earthquake potential remains extant. This crack might represent an incipient activation of strain that has been accumulating over decades or centuries. In effect, It may be part of tectonic rejuvenation, stress that has lingered in the crust, finally finding a path to express itself. More disquieting, the observed crack might be a precursor, a flush of small slips, micro-fracturing, crack propagation, preceding a larger release in the near future. Engineers in the region must contend with the unpredictability. Structures built near or above such zones may need reinforcement, repositioning, or abandonment. Bridges, utility lines, pipelines, and hiking infrastructure may all see differential motion. A crack that widens centimeters per year may shift footpaths sufficiently to damage pavement, destabilize anchors for guardrails, or twist foundations. More abrupt motion could sever lines entirely. Beyond physical infrastructure lies the human dimension. Grand Teton is not a remote wilderness detached from visitors. People hike, camp, take scenic drives, wander along ridges, parking near vistas. A sudden slope collapse, rockfall, or enlargement of fissure zones could endanger life, especially if it occurs without warning. While emergency protocols exist for earthquakes, a slow emergent hazard like this may catch visitors and managers off guard. Communication of risk becomes important. Lay people observing the crack may misunderstand its dangers, discounting it as scenic or a curiosity. The USGS warning must, not just scientifically but publicly, convey urgency without causing panic, emphasizing that the hazard is real, though not yet erupting catastrophically. Monitoring stations, signage, access restrictions, and education campaigns may be required to keep visitors and local communities safe. The crack also offers scientists a rare living laboratory. It offers a chance to study fissure propagation, interaction between surface and subsurface deformation, and coupling between fault slip and fluid migration. Real-time data could illuminate how stress transfers in mountain faults, how cracks grow, and what precursors signal acceleration. Though risky, the opportunity to better understand these processes is precious. The better the models, the better future warnings may become. Even so, science faces limits. No instrument can yet read quantum breaks of the crust far below. No model can confidently determine when creeping damage turns into abrupt failure. Uncertainty is intrinsic. That means planning must lean toward conservatism, assuming worst plausible scenarios, building redundancies, and maintaining flexibility. The crack demands humility. The ground beneath our feet may hold more surprises than anticipated. Given all this, how should local and federal authorities respond? First, expand monitoring. Place new GPS stations, borehole strain meters, and tilt meters flanking the crack. Use INSAR satellite passes to detect ground deformation, even micron scale. Fly laser altimetry to map changes in relief over time. Continuously monitor groundwater pressure and precipitation infiltration, as hydrological influence may accelerate crack growth. Second, hazard mapping must be revisited. Regions near the fissure require fresh zoning assessment, potentially restricting construction or infrastructure expansion. Trails, campgrounds, viewpoints might need rerouting. Critical infrastructure should avoid fault-proximate zones. Long-term planning should account for possible expansion of deformation zones. Third, early warning thresholds must be defined. At what rate of widening tilt or strain accumulation should evacuations or closures be triggered? Establish confidence intervals so that precautionary measures can be taken well before failure. Because the process may accelerate dramatically, such thresholds should err on the safe side. Fourth, public communication is crucial. Inform visitors and nearby communities about the crack, what it means, and signs of danger. New cracking, rockfall, fresh ground motion, sudden popping sounds, shifting foundation. Distribute maps, set signage, restrict access to unstable areas. Encourage reporting of unusual ground changes by hikers, rangers, locals. The fissure in Grand Teton may seem today a dramatic but localized geological oddity. Yet it is a symptom of force deep in Earth's crust, of strain-seeking expression, of a system that may be waking. That the USGS issued a warning suggests scientists believe this is not merely a curious break, but a portent. The danger lies not just in what is seen now, but in what may come. Accelerated rupture, expanding fissures, cascading fault slips, slope collapse. One must remain cautious, for geological systems rarely announce their rhythms in predictable ways. Still, recognition of the warning is the needed first step. The danger is that the fissure becomes a prelude, not the principal act. In the mountains, where gravity, rock strength, water, and fault stress intertwine, a crack is not inert. It is alive. And in this place, that life may grow. The Grand Teton crack is more than a wound in the landscape. It is a call to attention from the Earth itself. The ground is reawakening, reasserting its tectonic energy. If humans heed it, with careful observation, planning, and respect, some hazard can be mitigated. But if dismissed, it may remind us how small our constructions are in the face of shifting plates. The warning stands. This is more dangerous than it looks. Beneath the magnificent skyline of Grand Teton, the fissure stands as an evolving symbol of Earth's volatility, a living fracture cutting through the illusion of geological permanence. As geologists continue their fieldwork, they are discovering subtle nuances in the rupture's behavior that extend beyond the initial alarm. Instruments have recorded faint tremors, imperceptible to humans, rippling through the surrounding crust, hinting that the forces beneath are still active. These microseismic events often serve as preludes to larger fault adjustments, the crust releasing pressure in delicate increments before deciding whether to rupture violently or subside into temporary stillness. Every small vibration tells a fragment of a deeper narrative that has yet to conclude. The crack's orientation itself offers clues. It trends roughly northwest to southeast, aligning with known structural weaknesses of the Teton fault system. This alignment suggests that the fissure is not random, but a surface manifestation of long-term tectonic stress stretching the valley floor. Nearby ridges exhibit minute uplift, while some segments of ground appear to be sinking imperceptibly. This differential movement indicates the possibility of block tilting, where crustal sections pivot slowly around deep fracture planes. If such tilting continues, it could reshape drainage patterns, redirect streams, and alter the balance of ecosystems rooted in those slopes. While the crack has drawn much of the public's attention, scientists are equally focused on what's happening underground. Magnetotelluric surveys and ground-penetrating radar have begun mapping subsurface resistivity changes, subtle variations that often signify the movement of fluids through rock. These measurements show a band of anomalous conductivity beneath the fissure, implying that groundwater or possibly geothermal fluids are migrating through newly opened channels. Such migration can further lubricate faults, reducing friction and preparing the ground for more movement. The same water that carved valleys over eons might now be hastening the separation of the very crust that holds those mountains aloft. This evolving situation has also prompted comparisons with other sites where similar surface ruptures have preceded significant tectonic shifts. In parts of the Basin and Range Province to the south, small fissures once dismissed as minor collapses later developed into fault scarps tens of feet high after cumulative strain release. The resemblance is unsettling. Although the Teton environment differs in composition and hydrology, the mechanical process is eerily familiar, stretching, fracturing, and eventual readjustment of the Earth's crust to accommodate underlying forces. Meteorological factors add another layer of complexity. The Grand Teton region experiences rapid seasonal transitions, where snowpack, meltwater, and temperature swings exert alternating loads on the surface. When meltwater infiltrates deep cracks, it exerts hydraulic pressure that can widen them. Then, as freezing returns, that trapped water expands, prying the walls apart further. The cycle feeds on itself, magnifying the structural weakness with every season. Over years, these oscillations can transform what began as a hairline fracture into a deep geological wound. Meanwhile, the aesthetic serenity of Grand Teton stands in stark contrast to the invisible drama unfolding beneath it. Visitors see calm waters reflecting the jagged peaks, unaware that beneath those reflections the crust is under duress. Park rangers and geoscientists work quietly to balance public safety with scientific necessity, establishing monitoring zones and restricting access to unstable sections. Yet even their efforts highlight a humbling truth: nature cannot be contained. The forces at play here are older than the mountains themselves, operating on time scales that dwarf human memory. What emerges from this episode is not just a warning about potential geological hazards, but a lesson in perspective. The fissure reminds us that mountains, often symbols of strength and permanence, are transient expressions of movement. They rise because the crust is restless, because tension seeks relief, because the Earth is never still. The Grand Teton crack is not a mere anomaly. It is a continuation of the planet's ongoing conversation with itself, a reminder that creation and destruction are inseparable parts of the same process. As scientists maintain their vigil, the landscape waits, caught between stability and transformation. Each day of calm is not necessarily reassurance but intermission, the pause before another adjustment in the endless dialogue between rock, gravity, and time. Whether this fissure deepens into a scar that reshapes the range or slowly seals beneath sediment, its existence has already redrawn the map of understanding. The Earth has spoken, and for those willing to listen, the message is clear. Even in places that appear immutable, the forces of change are always at work, quietly sculpting the future beneath our feet. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on the USGS warning and what do you expect will happen next? We want to hear from you. Thank you for watching and see you next time.